Well, welcome. Again, my name is Mr. Murphy, and in this video we're going to be continuing what we did yesterday with where we left off at with learning more about end behavior polynomials. So let's start by looking at an example. So in this first, or I'm sorry, at a warm-up. And so in this warm-up, I want you to make sure that each of these are in standard form. If they're not in standard form, get them in standard form. And then I want you to identify what the leading coefficient would be. So why don't you guys go ahead and pause this video and do this warm-up just to kind of refresh your memory as far as what we were doing yesterday. All right, let's see how you did. So for that first one is already in standard form. Remember, standard form means it's the exponents are going in descending order with the largest exponent first. So here the largest exponent is 2, then we have an exponent of 1 and no exponent. So the degree goes from 2 to 1 to 0. So the degree of that polynomial is 2. Didn't ask for that, but that's just a review. But the leading coefficient for this would just be 1. Do not say x squared. Do not say 1x squared. A coefficient in and of itself is only a number, no variables. So do not include any variables when we ask for a leading coefficient. So the leading coefficient would just be 1. The next example, we have to put that in standard form. So in standard form, I would start with the 2x to the fourth because that is the largest degree. When you look at all the terms, that's the term with the largest degree. So we'd have 2x to the fourth, then going in descending order, it'd go to minus 3x cubed plus 5x squared minus 6x plus 1. And the leading coefficient for that polynomial then would just be 2. And lastly, we would have, so that one there, we have the 7x cubed, but the rest of it is not in the correct order. So then we'd have minus x squared minus 9x plus 12, with the leading coefficient then being 7. So hopefully that was a good refresher as far as what we were doing with leading coefficients and getting things in standard form. The only thing that we didn't ask there that you should also be remembering is that idea of what the degree of the polynomial would be. And so the degree of each of those would be, the first one again would be 2, the second one the degree would be 4, and the last one the degree would be 3. Remember also yesterday we talked about how to tell from just like by looking at that leading coefficient and actually the leading term as a whole, as far as how we could tell if the graph is going to increase from left to right or decrease from left to right, which direction the graph is going. So we should be able to get a good idea of what the graph looks like just from that leading term. And that's what a lot of this next lesson is also going to be, or this second part is going to be dealing with. All right, so looking at this equation, this polynomial, we're going to look at a table, and I did get an idea of what the graph would look like by the table. So here, what we're going to do is we would put some numbers in for x, like -3, -2, -1, 0, 1, 2, and 3. So we put each of those individually in for x and figure out what the y value would be. And so from the y values, we can see there where the graph is going to be increasing or decreasing at. So we can see that it goes from -11.5 to 6 to 4.5. So from a -11.5 to 6, it's increasing, but then from 6 to 4.5 to 2, it's going to decrease. Until we get to that 2, then it's going to go, after the 2, it's going to increase again. It's going to go from 2 to 4.5 to 6. But then after the 6, it's going to decrease again from 6 to -11.5. So we know the graph is going to fluctuate. It's going to go up and down at some different points. Now, there's a typo here. So let me just fix that. But this graph, so we would identify what we would call turning points. So turning points are where this graph is going to change direction. So we could see that we would have turning points from where x is -2 to where x is 1. Okay, so that's where our first turning point would be. We had to have another turning point from where x is -1 to 0, because that's where it's going to change from being decreasing to increasing. We'd have another turning point from when x is 1 to where x is 2, because that's where, again, it would change from being increasing to decreasing. So we'll look more at the turning points when we see the graph. But the other thing I want to identify is the fact that what we did in the previous video is we could see how this graph is going to look as far as its end behavior. We know that since our leading term is negative, or the leading coefficient is negative, we know that the right side of the graph is going to be going down. Okay, remember that from yesterday. So the right side of the graph would be going down. We know that since the degree is 4, it's an even degree, we know that then they would both be going the same direction. So as x approaches positive infinity, so the right side of the graph, as x approaches positive infinity, the y values would be approaching negative infinity. And as x would be approaching negative infinity, so the left side of the graph, y would also be approaching negative infinity. So if we were to actually graph that function, it would look like this. So we can see that yes, both ends of the graph are pointing downwards. And here we have our turning points. Now those turning points, we're going to come up with a better term for those. The turning points we could refer to as relative maximums and relative minimums. Okay, we've talked about a minimum for the graph when we dealt with quadratics. So the lowest point or the minimum point of a quadratic would be where the vertex would be the lowest point. Okay, or we could have that vertex, remember, having a maximum point. And so we've talked about maximum and minimum points before. But sometimes we don't have, we might have a graph that goes infinitely up and down. But if we have kind of these little change in directions, these turning points, we could have, instead of we may not have an actual maximum point if it continues to increase infinitely, but we might have what's called a relative maximum, where it changes direction before it goes infinitely up, or it changes direction at a lowest point before going infinitely up. So we have relative minimums, relative maximums. So the 2 points, so now we don't know the exact values. Now technically, those 2 points would be the actual relative maximum points. Because if I were to just look at that graph, at just that section there, we would say that that would be the relative maximum in just that section. Or if we were to look at a graph, the graph had just, let me erase that part, just between those 2 pieces there, then that second point would be a relative maximum. So we would have 2 relative maximums. So now we would say those relative maximums would be near the coordinates negative 2, 6. We don't know the exact value, but we know that it would be near the negative 2, 6 and positive 2, 6. And the relative minimum, there's only one relative minimum. Again, in order for it to be a relative minimum or relative maximum, it has to change direction at those points. So that relative minimum would be near that point 0, 2. Okay, so we have 2 relative maximums and we have only 1 relative minimum. Because again, it has to change direction at those points to be a relative maximum or to be a relative minimum. So you want to make sure you get those 2 terms in your notes. And what I would just say is that for a relative maximum, it's a highest point where it changes direction. And a relative minimum would be a low point where it changes direction, going from decreasing to increasing. Or a relative maximum would be a point where it changes from increasing to decreasing. All right. Let's look at this one. It says graph the polynomial and identify key features and sketch a graph. And so what we're going to do is we're going to identify, so we can use a table to estimate the turning points. So we can see that the turning points occur at about negative 2, negative 8, and at about 1, 4. And the reason why we can see that is because if you look at the values, so the values for y go from 0 to negative 8 and from negative 8 to negative 6. And so it's changing direction, going from increasing to decreasing right here. Okay, because before that, from 0 to negative 8, it's increasing. From negative 8 to negative 6, it's decreasing. So it changes direction. So we would have a turning point at negative 2, negative 8. And then we could see that it goes from negative 6 to 0. So that's increasing, and it continues to increase from 0 to 4. But then after the 4, it decreases. So the other turning point would be at 1, 4. Okay, so we need to make sure that we can look at a table and know where the turning points would be. Okay, so that's where it changed direction from being increasing to decreasing or from decreasing to increasing. So we'd have 2 turning points. And we can see from the original polynomial that since it's negative, so what we have here is, again, we can do our 2 blanks. Since it's negative for the leading term, for the leading coefficient, it would be going down from on the right side of the graph. And since it's an odd exponent, they're going to be going in opposite directions. So the left side of the graph would be going up. So we would describe that as x approaches negative infinity. So they're starting with the left side of the graph first. As x approaches negative infinity, the graph, the y values would be approaching positive infinity. And as x approaches positive infinity, so the right side of the graph, the y values would be approaching negative infinity. Okay, so that's how we can use all of that. So we can tie together both parts of this lesson now to figure out where the turning points would be and how the graph would be looking as far as the end behavior. And here's what the graph would actually look like if you were to type this in your calculator. So sure enough, we can see that The left side of the graph is going up. The right side of the graph is going down. We can see where those turning points are. And so that's the graph. All right. So in this example, what we're going to do is we're going to go through this one together. So this is, we're going to look at how we can use all of these descriptions to be able to come up with a sketch of what a graph would look like. Now, we don't have an actual polynomial here, so we don't know the exact shape of the graph, but we can get an idea of what the general form of the graph would look like. So here's how we're going to do that. So they talk about it being positive, so that means it's going to be above the x-axis from when x is negative infinity to negative 4, and from negative 1 to 4. So in those intervals, the graph is going to be above the x-axis. And then it's going to be negative on the intervals from where x is negative 4 to where x is negative 1, and from 4 to infinity. It's going to be below the x-axis. It's going to be negative on those intervals. It's going to be decreasing on the intervals from negative infinity to negative 2.67, and it's also going to be decreasing from 2 to infinity. And lastly, it's going to be increasing on only one interval from negative 2.67 to 2. Wow. All right. How can we put all this together to come up with the shape of a graph? That, if you try to tackle all of this at once, it's going to be a little overwhelming. So we're going to tackle this in parts. So the first thing we're going to identify is where are going to be the so we're going to estimate where are the x-intercepts going to be at. Well, how can we figure that out? Well, there's a couple of hints that they give us. For example, they tell us it's going to be positive from negative infinity to negative 4 and from negative 1 to 4. So remember, at the x-intercepts, it's neither positive nor negative. So we can identify those x-intercepts as being at negative 4, at negative 1, and at positive 4. Okay, so we can identify the x-intercepts. That's your first step. The second step is to identify or estimate. Well, actually, before we even do that, I like to figure out, because from those x-intercepts, we can even figure out where it's going to be positive and where it's going to be negative. So let me get my highlighter here. So what I'm going to do is I'm going to highlight on this graph where it's going to be positive and where it's going to be negative. And so it's going to be positive on the interval from negative infinity to negative 4. So that means this section, the graph is going to be positive. It's also going to be positive on the interval from where x is negative 1 to where x is 4. So here's where x is negative 1 to 4. So it's going to be positive. So it's going to be somewhere in that region. Okay. Now it's going to be negative on the interval from negative 4 to negative 1. So after we get these x-intercepts figured out, we can figure out where, by the description, we can figure out which regions the graph is going to be in. Okay, so now we're going to go to step 2. So step 2, it says to identify or estimate where the turning points would be. So the turning points are going to be where it goes from decreasing to increasing. So it says that it decreases on the intervals from negative infinity to negative 2.67. So that means it's going to be decreasing. We can actually see from our graph that, it's going to start over there in the top left corner, and it's going to be coming down. It's going to go through negative 4, but it's going to change direction as soon as we hit negative 2.67. And it's also going to be decreasing from 2 to infinity. So I'd have another, we could put a dashed line there, another dashed line there where x would be 2. Because from 2 to infinity, it's going to be decreasing as well. And then we can stick with those same dashed lines because we can see then that in between those is where it should be increasing. And sure enough, it says that it's going to increase on the interval from negative 2.67 to 2. And we already have the end behavior. So the end behavior we know. So the top left corner, it's going to be going up because, again, the end behavior, if you want to look at it this way too. Let me change to a different pen here. So from the end behavior, we can see that the far right there, that the graph is going to be going down. We see that here it's going to be going up. Okay, so again, we don't know the actual equation, so we don't know what the leading term or the leading coefficient would be, or what if it's an odd or even exponent. But based on this graph, I could identify the fact that since they're going in opposite directions there on the two ends, we know that this is an odd degree polynomial. And since the right side of the graph is going down, I know that the leading coefficient would be negative. All right, so we've identified that. So now we can identify, or we can sketch the graph. Now again, this graph, there's a lot of different ways you can sketch this graph. So the way that they did it here is they have that little curvy line looking like that. Now you might have something that looks a little bit different. Okay, oops. I just want to erase these arrows here. Okay, whoops. So yours might look slightly different. So for example, maybe you would have something that would look like this. I want a pen. Here we go. And then it would come up, go through that point. Maybe yours goes higher. But as long as you have the right shape, that's all that matters. Okay, that it flows through those regions that we've identified. That's what we want to make sure that we have. All right, so I want you to try this one on your own. So again, the first thing I would do is I would start by identifying what the x-intercepts are. And then just use your pencil or pen just to shade real lightly where it's going to be positive, where it's going to be negative. And then use a dashed line to figure out where it's going to change direction. And after you have all those pieces, then you can just sketch a line that's going to meet all of those criteria. So why don't you guys go ahead and pause the video and try this one on your own. And when you hit play, we're going to go through and walk through it together. So go ahead and pause this to try this on your own. All right, let's see how you did. So again, the first step is we're going to identify where those x-intercepts at. So our x-intercepts would be at, so it's positive on the intervals from -2 to -1 and from 1 to 2. So from -2 to -1, it's positive. So we'll shade in a second. And from 1 to 2, it's positive. All right, so let's shade those regions. Let me switch over to a highlighter here. So again, it's positive in between where x is -2 to where x is -1. So it's positive here. So in that region, it would be positive. It's going to be positive, again, in the region from where x is 1 to where x is 2. So it'll be positive in that region. We know it's going to be negative in the other intervals. It's going to be negative from -infinity to -2. So in this area, it's going to be negative. We know it's going to be negative in the interval between where x is -1 to where x is +1. And it's going to be negative from 2 to infinity. Okay, next we're going to figure out where does it change direction at. So let me just change pens here. So then it says that it's going to be increasing on the intervals from -infinity to -1.5 and from 0 to 1.5. Okay, so it's increasing on those intervals. So from -infinity to -1.5. It's going to increase. But then as soon as it hits 1.5, it's going to change direction. But then it's going to increase again on the interval from 0 to 1.5. So 0, so it's going to be hard to see here, but 0 would have another change of direction because from 0 to 1.5, it's going to be increasing. All right, and then it's decreasing on the intervals from -1.5 to 0 and from 1.5 to infinity. So now we should have enough information to be able to sketch a graph. So we're going to have a line that's going to come from -infinity. It's going to go through here, and then it's going to come down and go up. Maybe you have it go up higher. It doesn't matter. As long as your graph, and then we want to have arrows, as long as our graph looks something like that, that's all we need. Okay, so hopefully you had a graph that looks similar to mine. At least was in those regions, had those x-intercepts, it would change directions at those dotted lines. That's what you need. All right, so to end, we're going to end this lesson looking at some story problems and how we can apply what we've learned to story problems. So it says, in science class, Abby mixes a fixed amount of baking soda with different amounts of vinegar in a bottle capped by a balloon. She records the amount of time it takes the gases produced by the reaction to inflate the balloon, and this actually works. Fun little experiment if you haven't already done something like this. But from her data, Abby created a function to model the situation. So for x quarter cups of vinegar, it takes, and then they give us that formula, that many seconds to inflate the balloon. How long would it take to inflate the balloon with 5 quarter cups of vinegar? Okay, now before we get started with this, we want to make sure we know what x and y represents. So x represents the number of quarter cups. Okay, so the number of quarter cups of vinegar. And our answer is how long it would take for the balloon to inflate. So when it says how long would it take to inflate the balloon with 5 quarter cups of vinegar, that means we just replace x with 5. That's all you got to do. every time, so take out your calculator, plug in x, so we'd have negative 0.12 times 5 cubed plus 5 squared minus 3.38 times 5 plus 13.16. Hit enter, and that'll give you your answer of how many seconds it would take. And when you do that, there's the graph. We'll get to the graph here in a minute. But when you do that, you get x, you get your answer of 6.3. So it takes 6.3 seconds to fill the balloon when we use 5 quarter cups of vinegar. All right, so next, we're going to answer this question. It says, what do the x and y intercepts of the graph mean in the context, and do these make sense? Okay, so that's where the graph comes in. So when we look at the graph, and by the way, we can figure out the y-intercept without even having to look at the graph, because the y-intercept is just our last number, the number that doesn't have an x. Because if you think about it, the y-intercept is where x is 0. So if I put 0 in there for x, it will wipe out everything else, leaving me with 13.1 seconds, 13.16 seconds. So you can always identify the y-intercept super quickly by just putting 0 in for x. It's a little more difficult and more challenging to find the x-intercept, so that's where the graph makes it a lot easier. So we can see in this situation that the y-intercept is 13.16 and the x-intercept is 6.585. Now, what does that mean in the context of the problem, and does that make sense? So remember, x represents the amount of vinegar. So according to this graph, the x-intercept would not, or the y, let's start with the y-intercept. The y-intercept wouldn't make sense, because the y-intercept would mean that with 0 amount of vinegar, so if you didn't put any vinegar in the balloon, it would take 13.16 seconds to inflate. Okay, that's not going to happen. Just having the baking soda in there without vinegar is not going to inflate the balloon. So the y-intercept doesn't make sense. Let's see if the x-intercept makes sense. The x-intercept at 6.585 means that if we were to put 6.585 quarter cups of vinegar into the balloon, it would take 0 seconds to inflate, meaning as soon as you put it in, bam, it's inflated. That doesn't make sense either. So we would want to leave those off. And so that's all this is saying, is that the x-intercepts and the y-intercepts don't make sense in the context of this story problem. So as a result, we're going to have to limit the domain and range when considering that model. We're not going to actually use the x and y intercepts. It's going to be in between there. All right, so I want you to look at this problem. Now, I want you to try this one on your own, but we got to be very careful. So I'm going to point something out for this one. So it says Danielle is engineering a new brand of shoes. For X shoes sold in thousands, that's really important, in thousands, a profit of, okay, so that equation, that polynomial represents the profit, and that profit is in $10,000s of dollars. Okay, so when you do this, you might get when you see the answer, it might look slightly different from the answer you get, and I'll explain that afterwards. Okay, so I want you to try this on your own. But first, you want to make sure you want to know what to put in for X. So it says, how much will be earned in profit for selling 1,000 shoes? Remember what X represents. X represents the number of shoes in thousands. So 1,000 shoes would be 1,000. So we want to put just 1 in for X. Do not put 1,000 in for X. If you put 1,000 in for X, we're referring to 1,000 shoes, or 1,000,000 shoes. Okay, that's not what we're looking for. So we're just looking for where X is 1, because where X is 1, that represents 1,000 shoes. So put 1 in there for X and figure out what the profit would be. Now remember, the profit is in $10,000s of dollars. So see if you can figure that on your own, and then graph it and see if you can figure out whether or not the X and Y intercepts would make sense in the context of this problem. So go ahead and pause the video now and see if you can't figure these out on your own. All right, let's see how you did here. So first off, again, we use X, we replace X with 1. When you do that, you get 14 as your answer. And we need to make sure we know how to interpret what that 14 means. Remember, the profit is in $10,000s of dollars. So if we take 14 times 10,000, that really represents what the profit would be, because we have 14 10,000s. So 14 times 10,000 is 140,000. So 1,000 shoes would be a profit of $140,000. Now we got to figure out what are the X and Y intercepts. So the X and Y intercepts, you can see from this graph that the X intercept would be at negative 0.861 and a positive 1.915. Now where x is negative 0.861 does not make sense. Okay, because x, remember, represents the number of shoes. She's not going to have a negative amount of shoes. Okay, so let's look at the other x-intercept, 1.915. So that means if she sold 1.915 thousand shoes, so again, x is in thousands, so if she sold 1,915 shoes, she would have a profit of $0. That doesn't make any sense. Where x is 0, y is 10. That means that if she sold zero shoes, she would make 10 thousands, or $100,000. That doesn't make any sense either. Okay, so the x and y intercepts do not make sense in the context of this problem. All right, so that's it. So just in summary, so you want to make sure you understand. So take away from your notes, you want to make sure that you have these in your notes. Or what I've been telling my students is sometimes it's good just to have like a cheat sheet that has some key information on it. So for this first lesson, for lesson 3.1, this would be some key things that you might want to have in that short little summary, where how to figure out what the end behavior would be based on our leading coefficient and the degree of the polynomial, and identifying the relative minimum and relative maximum. Again, that's where it changes from decreasing to increasing or increasing to decreasing. And yeah, so if you have all of those things, those are the key things that you want to be able to take away from this first lesson.